Hello. Oh, wow. Okay. Hello, everybody. Hi. Welcome to the second ACM SIG-IR SIG KDD school, Africa School for Machine Learning for Data Mining and Search. Very happy to see you all here this morning. I'm Ben Carteret, and I'm really pleased and honored to be able to support the school. I am the chair of the steering committee. I'm chair of the ACM SIG-IR, which helps to fund the school. And I'm the dean of the program. I'm not sure exactly what that means, but that's my title. So, I'll be here all week. I'll be sitting here in the front, looking at all the presentations and talking to all you during the breaks and labs. And yeah, I'm really excited about this. I see a lot of familiar faces and a lot of new faces. We've had a lot of growth since last year, so that's exciting. And we have a really good program as well, starting today with Introduction to Search Technologies by Charlie and Zeynep here. So before we get started, Hussein's going to give some announcements, and then we'll jump in directly to the program after that. So thank you.
Thanks, Ben. Just some very quick announcements on behalf of the organizing team, who are very quietly sitting here, Maria Keat and Tamaril Sayed up there, besides Ben, and one of our other colleagues will join us tomorrow. Quick announcements. The most important thing to know is, where is the toilet? So I'll start off with a small apology. As a growing university, we're always going through renovations, and the one renovation we're doing at the moment is we're renovating all the toilets in this building at the same time. So there are two sets of toilets that you can get to fairly easily. One is on this level. If you walk around on this floor and you go into the building next door, which is the Otto Bates building, there's a map in the program as well. And just to the right, there are toilets down a short corridor. Or if you go down to the ground floor and out the front of the building where you probably came in, and you're also into the Otto Bates building, and there's a whole lot of toilets on the ground floor there, right? So you've got to go next door to go. This seems like old school. I had 4 announcements to make. The second one is we gave you a small piece of paper to do a quick survey on which session you are likely to attend from Wednesday to Friday. Please tick those sessions and give them back to us. This is not in any way definite. It's just for us to get a rough sense to make sure that we have the right group in the right venue in terms of sizes, right? So you can think about this all day, and by the end of the day, please give that back to us. We'll have a box somewhere at registration. The third thing is there's a Twitter hashtag that's AFIRM 2020 for anybody who wants to tweet, right? And that's also listed on the front page of the program, so you should not miss that. And I know I'm going to forget the fourth thing, right? What was the fourth thing? And the fourth thing is, if you're trying to get into the Wi-Fi, all right, on the back of your name tag, every person has 2 sets of login details. One set of login details allows you to get onto something called UCT Guest. And every person has their own account on UCT Guest, and you can use that if your institution does not have EduRoam. If you have EduRoam, it ought to work just instantly by itself. There's a second set of login details which you will use during the lab sessions in the afternoon. And there's a very small print mini program on the back for those people who have extremely good eyesight, but it basically shows you the venues for all the different sessions. Right? So at this point, I'll hand it over to Charlie. Thank you very much.
Thank you. Thank you. Okay. All right, can everyone hear me? Okay, normally I wouldn't use a microphone, but I'm told that I have to do that for recording purposes, so let's see if I can put it there. Okay. So my voice is coming back to me in a very strange way, so do I sound all right to you? You can hear me fine. All right, great. So this is the summer school on information retrieval and data mining, machine learning for information retrieval and data mining. And sort of information retrieval is basically the theory underlying search technology. So we have 2 lectures this morning to give an overview of information retrieval, and the first half is really to talk about how this fits in to the big picture of kind of how things work in the world. So what are we actually trying to do here in this summer school? How are we going to apply the theory that you're going to be learning and things like that? I'm Charlie Clarke from the University of Waterloo in Canada. I'll have a little bit more information about that. My colleague is Zeynep Yilmaz. She is a graduate student or just recently finished graduate studies at the University of Waterloo, and I'm doing all of the talking this morning, blah, 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 blah. And then this afternoon you will have labs, which is much more interesting than me talking, and Zeynep is the person that's done all the work on the lab. So the really interesting part of today is not me, it's Zeynep and the lab, so that will be fun in the afternoon, okay? So me talking is not so much fun. This is where we're coming from. It is winter there. So this room is fantastically warm as far as I'm concerned. And it's sort of, that is Canada. We are in that part of Canada, as close as we can get to the United States without actually being in the United States. And so that's where we're from. Who am I? I've been working on search technology for longer than some of you have been alive. As a graduate student, and occasionally I work in industry. I spent a year at Microsoft just when the Bing search engine was being put together. I just spent, very recently, less than 2 years ago, I spent just over 2 years at Facebook working on Facebook search. And then also, I've spent lots of time doing academic research, the theory of how to do search technologies. And so the tutorial is coming at you mostly from an academic background, but I've really worked on search engines in large-scale companies, especially at Facebook, where I was 2 years there and sort of deeply involved in their search technology. So we're getting a bit of both, from both industry standpoint and from a kind of academic theoretical standpoint. Okay, so I've gone into the theory and picked out the parts that we actually use in reality, and then come and tell you about that. Great. So a while back, I wrote an introductory textbook on this subject, along with a couple of colleagues, one at Google and one at the University of Waterloo. And so there are a lot of examples and figures taken from that book. And most of the things that I have are online. So this will be in your slides, but there's basically all of the introductory material from the book The core introductory material is available online, so you can go if you're something here that you want to learn more about, you can go there. Okay, so there's a lot of figures and slides from this, and this is not the ideal app. Well, it's not bad. It's a fairly close room, right? So feel free, please, to ask me questions as I go along. If you don't understand something, we have lots of time, so I can answer them. You know, in a minute, Doug will demonstrate what it's like to ask a question, I think, at some point, and that will get everybody kind of a little bit more interactive, hopefully, right? All right. So what are we talking about when I talk about search technologies? Well, there's good old-fashioned web search, Google being, I guess, the most widely known brand of web search in the world. There's also Bing, which works worldwide, and we have multiple people here who are involved in various levels at the Bing search engine. I think actually you're part of the research team behind the Bing search engine. Nick and Bhaskara, who you will hear from on Friday. Around the world, though, there's lots of search engines. If you're in China, Baidu is the search engine, one of the search engines available, although a lot of stuff happens on WeChat. If you're Russian, Yandex is the search engine there. That's local to that. There are not a lot of regions that have search technologies. Most places in the world, Google or Bing or something. There's also something like DuckDuckGo, which is something that tries to not track information about people, right? In other words, it tries to do the same thing that Google does, but without, let's say, knowing so much about you. That's the idea of that. So there's lots of still web search in the world, so that's what we're talking about there. But there's a lot of other places where search engines show up. And a very important place that search engines show up is for e-commerce. So I'm told here in South Africa, bid or buy is the equivalent of eBay. I don't know, somebody here can tell me if that's true, okay? Amazon is sort of worldwide as well, right? And both of these, you can see, have search boxes, right? And this is the same, underlying this is the same basic technology that you'll see underneath Google, underneath Bing, underneath any of these search engines. So that's what I'm talking about. There's also social media search. So Twitter and Facebook. Facebook looks a little different. This is what it looked like back when I was working on it. Facebook looks a little tiny bit different now, but still has the same underlying search engine up there. And so on the web search engines, you're searching the web, of course. On the e-commerce search engines, you're searching a collection of products, okay? Here you're searching social media posts and images and things like that. And then there's a lot of other places, app search. Here you'll see I've done all the search boxes. So there's a search facility. This is the App Store for iPhone, but there's a store for Google as well, and that's going to have, so not for Google, but for Android as well. This is Spotify. I was doing these slides as a demo, and somebody said, do you really search for Smoke Dog? And I'm like, no, I don't actually use Spotify, so this is something I grabbed off of an image of somebody else's search. But Spotify will have a search, and that's the search. You can search then by music or lyrics or anything like that. And then in the world, there are more and more of these smart devices here. And actually, there's a search. You can't see the search box because you're not typing into it. You're speaking at it. But there's search technologies underlying that as well. So all of these kinds of places. And the theory is common. The way that everything works is very common. But the things that you're searching are very different. So web pages. The important thing, the distinguishing things are that the web, the data, there's a lot of it. It's all over the place, and it's in all kinds of different formats, and a lot of it is junk that nobody will want to see again. Right? So web is very important. The quality of the results is very important. From the Product categories, right? If you're searching for things to buy, you want a really good fit with what you're trying to buy. You want really good fit with what you're trying to buy. You want a really good price for what you're trying to buy. And the really interesting thing about e-commerce search is that once you, especially something like where there's only one people, sort of consumer to consumer sales, once you sell it, it's gone, right? So the search engine has, the web. I show you a web page, you like it, I can show it to a million other people, a billion other people. A product, once someone buys it, it's gone. It's not in the search engine anymore, so you have to know how to take it out and put in, okay, this is a maybe not so cheap, but the same product for sale, right? And in all these things, they have special cases that have to be handled, but on all of these places, that wherever you go and you type something and you see a result, you get the same basic technology. And in fact, I don't talk a lot about recommendation here because we're focused today, I don't want to go too wide, but a lot of the technology, so if you go to something that is recommending that you buy something or you watch something or you listen to something, a lot of the technology is the same. So what we're looking at here today is the basic technology underlying all of these things that you use. If you use some of these, a couple of people have Apple machines. They have a file system, search Spotlight it's called, so you can search your computer. I don't use Windows that much, but you can do the same thing there. So that's what we're talking about. I just want to give you a space of the kind of technology we're talking about here. So all of these search boxes you see in the world are what we're on about today. Okay. So what are the pieces we're going to talk about? So search engine can be searching anything, but we have to find it. So somewhere in the world, if we're building web crawl, if we're building something like Google or Bing or Yandex or Baidu, we need to go out and get the data off the web. And that's a whole other set of things I could talk about. I'm not going to talk about that in detail, but we have to go out there. It's not a matter of just, I can do that instantly. A piece of software has to go around to every website in the world, find every website in the world, make a copy of that data, bring it centrally. It has to know, okay, something's news or something is something that changes rapidly. It has to know to go back and get that information over and over again. If it's something that doesn't change very often, like the web pages of the university here, it goes back less often, but it still has to keep that data. Right? And once again, it has to figure out what the good stuff is and what the stuff, that are trying to sell you scammy products or something like that. So separate all that data out. If we're doing e-commerce search, we'll have a product catalog, and that product catalog is going to change all the time, and maintaining that product catalog is a whole other problem. Right? If we have people selling different kinds of things, a book or something like that, we have to be able to figure out, that product and this product is the same product, right? There was somebody I was talking with a while back who was working on search technology for car parts, okay? And eBay in the United States, they have whole teams of experts that know that a combination switch for a 2010 Camry will fit on a 2009 Camry, but not on a 2011 Camry, right? They know that kind of stuff. That's so when I'm going to gloss over a lot of this stuff, but you need to remember there's tons of things, everything from just very careful categorization to machine learning technologies underlying all of these things. Same thing, social media posts. At Facebook, there's just a tremendous number. Facebook indexes and allows you to search every post anybody's ever made in the world ever. Okay, just a tremendous amount of data. And then if you're at somewhere that's doing something like music or something like that, there's lyrics and song titles in multiple languages, and people, there's endless problems. Things are in multiple languages, but people will search using like English characters, a language that doesn't use English characters, and you have to figure out the transliteration, and there's like a million things going on here, okay? So getting the data, I'm not going to spend a lot of time on, but it's just a tremendous bunch of problems there. There's indexing all that, and I will talk about that in some sense. You will get a sense of what's going on for indexing, and you will have a chance this afternoon to do some actual work in that area yourself. So indexing is figuring out how to find all this stuff. Once we have the data and somebody puts in a search, how do we actually find the data? And then how do we figure out which is the best thing to return to them? And I'll spend some time on that. I'll spend a lot of time on this here. And I'll briefly mention some of these other things. So I'm not going to spend a lot of time on that either. Okay? Yeah. Any questions? Anything at all? Yeah, oh, sure, yeah, hi.
Yeah, not really on what you have said. So
Yeah.
I just want to know whether we have access to this material after your presentation.
Oh, yeah.
I know whether I should.
These slides, oh, yeah, no, we'll have the slides.
Just listen to you.
I think the slides are already on. You should have gotten a small blue, yeah.
Okay, here. Okay, it's
Yeah.
here already.
Yeah. So sorry, yeah, I should have said that at the beginning. So everything I'm saying here, I think I changed them a little bit. Last night I said, oh, I should add this, but the most of it is there. And then also the book, the link to the book will have maybe 3 or 4 chapters about the core stuff. Okay, so there's plenty of stuff. So don't just relax. Okay, just relax and then follow the thing. Okay, but that's good. I got one question, so I can have now other people will feel like asking me questions, right? Okay. All right, and the thing that I really want to emphasize here is the scale that in modern technology, the scale of what we're talking about. Okay, so this is actually 2 pictures of Facebook's main data center in Prineville, Oregon. And these are data center halls here. And just to get you some sense of the scale of that building, that dot there that takes up a pixel or so, that's a car. Okay? So these buildings are enormous. And all of these buildings are filled end to end with computers. Floor to ceiling, end to end, multiple halls. So when people talk about, so I don't actually, I think people have very different backgrounds in here. So if I'm saying anything that you know really well, don't worry. There's probably someone in here that needs the explanation. And if I'm saying something that seems really difficult, also just relax, because we have a lab this afternoon, and in that lab we'll help clarify a lot of things. So, sometimes I'll say something that maybe is a little, easy for you, and maybe I'll say something that doesn't make any sense, and by the end of the day, I hope everything will make sense to everybody. So anyway, these things are filled here with machines, floor to ceiling. Now, this is Facebook, so a lot of this is doing social media type things. It's not all search, but in here somewhere are machines that do the search and things like this. And these buildings are absolutely huge. And in fact, each of these data center halls is almost like one computer, because all the pieces are very tightly interconnected with each other. So in terms of your laptop here, it's like having thousands and thousands, tens of thousands of these laptops, not with screens, but all stacked up, all communicating with each other, all with large amounts of, in the case of search engines, flash drive or disk. And there's whole other systems. One of these buildings is where most of the image data is stored. So if you have a video or something, you store it on YouTube or you store it on Facebook or something like that, you can go back years later and see that video. And there's a very elaborate system for minimizing the amount of storage that they use for that. So this is just, and so when people talk about storing things in the cloud, later on you're going to be working on notebooks that use Google Colab, where all the computers are out in the cloud. okay? So you're going to sit down in front of these notebooks and you're going to run Python code, and that Python code is not going to be running on your laptop or on a machine in the lab. It's going to be running out in the cloud. And so when people say it's out in the cloud, if you've ever heard that expression, that's nonsense. It's not out in the cloud. It's in there, in one of those computers in that building. So when you sit down, not in this building because you're Google, this is Facebook, but a building, Google has more buildings than Facebook that look like this, right? So if you're working in the cloud, you're not working in the cloud, you're working on a computer in one of those buildings somewhere in the world. In the case of what we'll do today, the computer is probably, I think the closest data centers are up in Europe, to be honest. So you're probably going all the way to Europe for Google. Okay. Okay, so how do we run search? How do we run search at that scale, where we're we're searching all the social media posts in the world or all of the web or anything like that? And I've started using a volcano model like this, and took me the hardest slide in this entire talk to make was finding that picture of a volcano, because I wanted it to look exact. I almost drew it. I wanted it to look exactly, because I wanted to show the lava down here and everything else. And it's surprisingly hard to find a picture of a volcano that looks like this, right? And I was thinking I should use this as an example in the lecture, because I said pictures of volcanoes, and I kept changing my query, and then most of them you had to pay for because it was art that would come with something across it. But this one was a U.S. government illustration of a volcano. Okay, so this is my explanation of how search engines work at scale. Okay, so down here we have all of the data that so this could be all the pages in the web. This could be all the posts on Facebook or Twitter. This could be all the products being sold on Amazon. This could be all the music on Spotify, right? And the idea is it's a little destructive, I suppose, but we want to come out of the top, just a little thing that you're looking for. We got to take all this data and we've got to funnel it up until we get the answer. So the pieces of the volcano are right at the bottom. Oh, sorry, I should say, right at the bottom we got billions of items. We got huge numbers. And then as we go up, we want to filter that down, right, to one small thing, right? So we're going to do some kind of basic retrieval to pull a pool of things out of here. I should have put a concrete example. Later I'll have a concrete example of tomorrow maybe, or later on the weekend, because I'll be here, if I'm here for a while, I want to do some kind of tour in Cape Town. So later I have the example, I should have put it earlier. I go to Google and I type Cape Town tours, okay? So here's all the data in the world, and I've typed in Cape Town tours. So there's something that has to look in that and find everything that's about Cape Town, South Africa, and something about tourism and something to do with me, and pull that out. So we'll end up with the billions of items in the world, and maybe thousands or possibly millions of those items. I'm going to be kind of vague here, because for some search engines I know how many numbers these would be. And there are really more layers than this, but we're going to get to the key layers here, right? So basically the first step is to go into that pool and pull out some thousands of things that might have the answer, that might be the thing I'm looking for, okay? And then there's some kind of ranking system that's going to take the thousands and millions of documents and filter them down to hundreds of thousands. And finally, I'm going to do some kind of re-ranking, and I'm going to get maybe the top. And all that matters is the top for a lot of applications, not all of them, and not image search, but for a lot of applications in search, the only thing that really matters is the first answer, or the second answer, or maybe the third answer. Like a lot of, so I'm starting with here, Cape Town tours, and what I want to get, and down here I have billions of documents, and at the top I have that one TripAdvisor page that lists the top tours for South Africa, and that's the thing I'm looking for. So the problem is, how do we get from here, where we have billions of things, to one thing that is the thing I really want when I go to Google or Amazon or somewhere like that? Okay. Now is the time for questions. If you don't understand what I've said up to this point, this is a good time to ask, because if you're confused, other people are confused too, right? No, we're all good. Or am I going too slow? I could go faster. Okay, that's good. Don't go too fast. All right. So 10:15, is that right? Is that, yeah, okay. So we got lots of time to go. All right, let's start simple. This is much simpler. Okay, this is really the key components. So yes, I've said, okay, data center, and it's full of machines, well, that's very complicated. So let's just get down to one very, very simple thing. And this will be actually very close to what you will do in the lab this afternoon. Okay, so instead of the huge data center with all this stuff, let's just get down to the essence of what we're doing. Okay, so we're trying to build a search engine, which is an interesting, this is machine learning for information retrieval and data mining, but there's actually quite a number of different components in here, of which machine learning is a sort of, I'm sort of building the background, so you'll see some of the machine learning later in the, because there's a whole lot of sort of database related things in here. There's a whole bunch of natural language processing related things in here. There's a whole bunch of machine learning things in here. And there's a bunch of human computer interaction stuff, right? So to build this whole end-to-end thing where we start with that pool of data, which is products or web pages or music or images, and end up with something that can find the answer, you have to put together a lot of different technology. But the key part of it is that we have a person up there, I guess, and that person has some kind of thing they're after. They're after a piece of music. They're after a web page. They want to go, oh, where should I go? Those of you who are local, maybe you can tell me. That's another kind of search engine, is to have someone locally recommend you where to go. But they have some kind of information need. They have some kind of thing that they're looking for, or thing they want to do. And they go to a computer, right? And they send off a query, Cape Town Tours, and it goes down into the data center or whatever, and that looks somewhere down in their collection of data. This is the collection of data here, and sends back an answer. And there's things changing all the time, new products to be sold, new changes to web pages, new music, new images, and things also go away. Like, so a page will go out of date, right? So this is the simple version, and we're basically going to do all this today on one computer, but you need to keep in mind that the real picture is that giant data center, okay? So query comes in, the search engine sends back a result, we have a collection of data that we're searching, and this is the piece that ties it all together. All right, so let's go really simple some more. And let's say, well, what do we want to do? Remember, we really have billions of things. We have really a whole lot of different things. But I have one page here. And it's the start of Shakespeare's Macbeth. And it has lots of interesting structure that is similar to, I'm going to use as an example for the different kinds of things that you see in products or web pages or something like that. So in the case of Shakespeare's Macbeth, let's pretend we're building a search engine for just Shakespeare, which is not a very large amount. It's a large amount of writing for one person, but not a lot of writing compared to the entire web. So we have lots of some structure here. We have people giving speeches, right? So we have a witch here, right? When shall we three meet again? They get the dramatic. We got some speeches, right? People speaking. And so I'm using this as an example. This could be titles of web pages. This could be products. But here we're going to work with speakers and speeches. And we also have things like stage directions and stuff like that, acts and scenes. So we have an interesting document here. And then what do we do with it? Well, if it was a web page, it would be, if this was a web page, this would be marked up with some kind of HTML. Here I'm going to mark it up with XML. But you need some kind of representation of your data like this. So it's not just a product, it's data, it's text that you can work with. Okay? This is XML. Okay? These days you will use, people know what I mean by JSON? Okay. Some of you do, some of you don't. Okay, JSON is another, it's another format for expressing data. You will be working with data in JSON today, but they're all the same thing in the sense of being able to take what you saw, which is a sort of abstraction of what everything should look like, and turn it into data that's a mix of kind of structure and meaning, things like speeches and speakers, and things that are just natural language text. Okay, so you want to think of your data as a mixture of structure and semantics and dates and prices and running times of music and things like that, and some kind of natural language data. English, Chinese, any language in the world. Okay. All right. So in order to rank stuff, we want to preserve both the structure and the language. So I said search technology, it's like natural language processing merged with database systems, because that's what it is. You have to represent both detailed structure of things, okay? So in general, to help with ranking, we want to know what are the titles, who are the authors, what are the dates, because, the title of something is, if I'm looking for Cape Town tours, something called Cape Town tours is likely to be a good thing, whereas the word Cape and town spread out, not so good, right? We want to know who wrote it. Dates are important because people like more recent things, and a lot of search applications, the most recent thing, we got two things that are almost as good or equally good. The most recent one is usually the better kind of thing. For the web, we want to preserve all our links, so we want to know what pages we're linked to, right? And for products, we preserve prices and models and sizes and things like that. Not just as text, not just as saying, okay, the shirt that we got this morning was a medium size, not just the word medium, but the concept that it is medium sized, okay? And so that a shirt over here that is called medium and a shirt where the size is M, they are actually one and the same thing. These are the kinds of things you have to understand when you're working with data, okay? So here we have this structure preserved, and that's what, so depending on the application, we're going to preserve the structure. Okay. So then, this is actually still a bunch of characters, right? FIR. So what we want to do then is we want to split it up usually into tokens, and you will, once again, all of these things I'm doing, you will do in the lab this afternoon. So you will have a bunch of text. You will see in Python how to tokenize it. You will see all of these things, okay? So as part of the full collection of Shakespeare, all the plays in order that they were written, right? We give a number to each. We split it up into words. That's called tokenization. And we give a number to each of the words. So, or the structure. So this word or here is at position. Shakespeare wrote a lot of words. Okay, 745,421, that or is at that position. Rain here is at 745,423. Okay, so think of all the words in Shakespeare laid out one after another, and I'm going to give each word a number. Okay, starting at 1. Actually, you think starting at 0 because it's computer science, you start everything at 0, but I think this started at 1 because I tend to use 0 to actually be something that says this is the start of the data. But anyway, so I think this is actually starting at 1, that number. So rain, second. Every single word in Shakespeare has been given a number. And then actually it's kind of interesting, these words. So in that collection, I have a collection, a guy called Bosak put the collection together in XML. And I took that collection and I tokenized it. And here is the frequency of tokens. So interestingly enough, this is what you'll always see with this kind of data. The structure of the data dominates the tokenization. Okay? So what's in Shakespeare? There's 107,000 lines, 833 lines of text. There are 31,081 different speeches, essentially, right? For some reason, the speakers and the speeches don't match. There's some odd things in there. I think multiple speakers say the same thing. But then we get into the words themselves. And so this is all in English. It was Old English, but it's all English. So the dominates, and all of the conjunctions and prepositions, right, dominate. Okay, so what I've done is I've taken all that text, I've just counted the number. All of the things, steps I'm doing, you'll do in a collection this afternoon in Python, and you'll go all the way to a search engine, so if you don't quite understand. So any questions on what I did there, where these numbers come from? Okay, so it's just a count of each token in the text. And the interesting thing is, if you take all these tokens and you put them on a plot like this, so I should have brought my laser pointer with me. I added pointers in the text with those red arrows that show up. Okay, so that along this line here, that dot way up there, that's the number of the. Well, actually, this is just words. I think I took the structure out. That's the thes in the collection. So there's somewhere between 10 to the 4 and 10 to the 5. This is a log scale here, and that's a log scale there. Okay, so the most frequent word occurs that often, and the least frequent word, of course, occurs once. Okay, so if I lay out the words by frequency and by rank, okay, I get more or less a straight line. Oh, there, thank you. Okay, yeah, that's the point I'm talking. So that's the, okay, and that's and that's of, I can't remember. But these are all those common words. And then all of the words, and then they tend to follow this line, and that's something called Zipf's law, right? Which says that the frequency is proportional to the rank, okay? Or sorry, frequency is proportional to the inverse of the rank, right? And that's just the way this kind of data works, and you'll see that for links to web pages. You'll see it at the character level. You'll see it in tokens in every language in the world. Language data, the kind of data that we work with in search, tends to follow this relationship, and it's a bit amazing because nobody knows why. Yeah.
I was wondering, is it not possible during processing of your data to eliminate some of these prepositions? Because there's a likelihood of
That's right. Stop words, good. You guys are you guys are way ahead of me, right? Yeah, we'll come to stop words in a minute. I'll show you about stop words. But yeah, eventually, so what they're talking about is if I'm searching, often the is not a very useful word all by itself. It's actually useful in combinations with other words, though. So you can't actually, in practice, totally remove it, because there used to be a long time ago a music band, and they were called The. That's the name of the band. So I can't take the word the out entirely, because then I can't search music by the, right? Well, The Who is another more famous band that, those by themselves look like unimportant words, but you put them by each other, then they're suddenly very important. So I'll come back to stop words in a minute, okay? But you're absolutely right about stop words. Right. So I just want to pop back, not there. I want to pop back for a minute. So here are all the words tokenized. What I can do if I want to look things up is the very basic way of looking things up is with something called an inverted index. And so this is sort of like the key underlying data structure for search engines. I mean, it's by far not the only one, but everything else kind of builds off of this in some ways. So what I've done here is I've said for every word, I've built a dictionary. So every word, and this is all in alphabetical order, so first is up there, and witches and witching and everything is in order. Okay, and what I do is essentially I'm inverting the tokenization. So I'm taking all that tokenization, which was basically 1, 2, 3, 4, 5, here's all the words, and I'm saying, okay, the word witch, right, all the places that it occurs are here, here's witch, and it occurs at position 1598, and then it doesn't occur until 27,555, and sometime later it occurs at 745,407. Oh, I have one already. Yeah. I guess I should use it now that I have it. So which occurs here, 745,407, until we get down right to the end as an occurrence at 1,245,276. And already I can use this for some really interesting things, right? For example, if I want to find the phrase first which, I essentially do a join, right, on, if you're familiar with database technology or terminology, I essentially do a join on first and which. So I essentially, in some sense, join these two columns, right? And at some point I'll discover that first here is just, that's 406, that's 407, so that tells me that's a place that first which occurs. So that's the kind of operation that I'll be able to do to find phrases like the, although that's not exactly how you want to do that. You actually probably want to do that one in advance, or the who or something like that, okay? So, and now in practice, this is probably not counting 1, 2, 3. It's probably a combination of a document number and a position in the document, okay? Ordered first by document number and then position in the document. Okay, so this is the 17th word of the first document. It's a pair that looks like that. Okay, so that's typically really what we do. We really don't do 1, 2, 3, 4, 5, but it's a good place to start to understand what's going on. Okay, so this is the you'll build one in the lab today. You'll go through and build one of these. Okay. So in research, and I'm going to now start to make occasionally a difference between building a search engine that is going to be used at Facebook or Google or Amazon or Spotify or Microsoft and something that is going to do research, okay? So in research, we almost always, first of all, case normalize things. So here is, use Shakespeare. I use Shakespeare because it's in my book. Okay, so some of these figures I took out of the book that I showed you, and I use Shakespeare in the book because it's in the public domain. So I don't have to pay, I have a lot of text that I don't have to pay anyone to use. There's nothing special about Shakespeare, it's just that it's a lot of text that was free. Okay, so here is Hamlet's soliloquy, to be or not to be, that is the question, blah, 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 blah. And you read Shakespeare and it always seems like very cliched, right? Because this is where all the cliches come from, the slings and arrows of outrageous fortune. And so we case normalize it. So you see we take all the punctuation out, okay, and we, in English, this varies a lot from language to language. In English, we take all the capital letters here and make them lowercase letters. The book has some stuff about working with a lot of other different languages. But anyway, this is English we're working with here. And then we do something called stemming it. And this is a place where research tends to vary more than industry. Industry, you have to be very careful with stemming because it can often, so what happens here, for example, is we have a word like arrows here that turn into arrow, right? So what we're doing is we're trying to say, oh, in English we have, you know, arrows and arrow, and they're really the same concept, they're really the same word. We have, you know, run and running and runner and runs, right, and ran, and those are all sort of run, okay? So in research, it's very common then to stem. This has been done with a stemmer called a Porter stemmer, right? And this will happen, once again, everything here, I think you'll see in the lab, you'll see some stemming take place. It might be hidden away, but it's happening, right? But what you get is things like here, you know, consummation turned into this, and, you know, yeah. Okay, and so we've distorted it. And then finally, in research, we often eliminate stop words. So this is, you know, so if you're doing experiments in machine learning or information retrieval or natural language processing, it's very, very common. And look, question T, nobler mind, suffering, sling, arrow, outrage, fortune, take, arm, see, trouble, a pause, end, die, sleep, say, end, heart, act, thousand, nature. I mean, what does this mean? If I should have shown you this first and asked you if anyone recognized it, all right? So this is what you do for research, okay? So if you look at most papers that work with natural language data, not just search and information retrieval, but almost any kind of natural language, they'll do heavy stop word, and that's because you do that for a very special reason. It's because it makes your evaluation measures that you're comparing against get better, okay? Reality doesn't make any advantage. Well, in commercial search, for example, you do things like stop word elimination, stemming, all that kind of morphological transformations very carefully, right? There are, you know, most groups that do commercial search will have a natural language processing team that will do some of these things that are much more lightweight and much more specific. So arrow going to arrows, probably okay unless the product name is arrows, in which case you definitely don't turn it into arrow, okay? So this is what happens in research much more. This is, you know, if you go to a commercial search, they do not do this heavy stemming and stop where they do some much more complicated and specific stuff. Okay, so that's what we do with our data. Okay. And I'll come back to this afternoon. This is just like the high level view of what's going on. So the bottom of the volcano, we saw the volcano. I said there's billions of items. You'll actually have a collection with billions. How much is in the Marco collection? So 8 billion. Yeah, so even the collection you're working with today will have 8 billion things in it. Okay, so when you go to the lab, you'll work with a collection called from MS Marco, Microsoft Research put it together. 8 million. 8 million. Okay. So never mind, it's trivial. Okay. But many of the test collections that I've worked with have billions of things in it. I haven't. Okay. So, but basically, the lowest level of volcano is going to work with some very simple statistics. It's going to work with the number of documents that contain a certain term. So the is not very important because in an English collection, most items are going to contain the. How frequently terms appear in the items, the length, statistics. So these are the typical low-level things. And then we put them together into something called TF-IDF ranking, which you may have heard about if you've read any of this stuff. And that's just a combination of a function of term frequency and a function of inverse document frequency, so that if things occur in something frequently, the inverse is small, right? But if it doesn't occur very often, the inverse is large. And we'll see an example. I'm not going to do it this morning, I'll do it this afternoon. There's something called BM25, and you will work with BM25 to see this afternoon. And that's an example of TF-IDF ranking. I'll show you why it's TF-IDF ranking. All right, so that's kind of the early introduction to the, sort of very simple. So let's go back, though. I want to go back, and I want to, these are the sort of core pieces that you're going to use this afternoon. I want to go back, though. I want to go back to the big picture at the large scale and show just very briefly all the pieces we're not going to get into. So the things I've done in the last 20 minutes, 25 minutes are things you're going to do this afternoon. I want to go back and look at all the pieces that we're missing to make sure you can see all this in a big picture from a commercial standpoint. So in practice, it's not just words and things like that, but even the lowest level, even the bottom of the volcano, is going to use features that are not just text. They're not just matching words. I think a lot of people think that search is just about matching the words in the text, and that's not it at all. So even at the lowest level, it's going to have something about geographic locations and things like this. It's going to have personalization aspects. Who am I? What do I like? And it's going to have information about quality. So for web pages, is it spam? Is it a popular page? Is it a high quality page? And things like that. Okay, and they're unrelated. So in some sense, quality is related to spam, but popularity is not necessarily related to quality. Homepage of an individual is high quality if you're looking for that person, but it's not very popular unless that person is, a popular person. Okay, so that's in practice. A query is not just. Here's the example I wish I had put in earlier. It's not just Cape Town tours typed into a box like that. Okay, those words. What also goes in there is this information about where I am. There's stuff about me. It's a better picture of me than I usually take. Okay, and it also, what's going into that box is not just the literal characters, but also a lot about the environment and context of the query, both in terms of the person asking the query and in terms of where that person is physically located in the world. Okay. And in fact, queries in practice in a real commercial search engine, right? If I type Cape Town tours this morning, right? Here's what is going to go in to that lowest level of the volcano. Okay? What's going to go in there is I'm at the University of Cape Town, South Africa, and that Latin long information. Okay? Knows where I am. It knows the stuff around this area. The words Cape Town, there's going to be a part of the system, a query understanding system, and it's going to go, wait a minute, Cape Town, that's not just the word Cape and the word town joined together. It's not. Nobody's wearing a cape. Okay? This is Cape Town. There's going to be a system that says, okay, that is a geographic entity, and here is all the information about that geographic entity. And that geographic entity is a city, and that city is in South Africa, a country, and here's information about the country. Okay? And then the word tour, rather than being kind of reduced with a stemmer, a commercial system will say, oh, okay, the related terms are, trips, guides, stuff like that. So that's going to go into the query as an expansion, and it's going to say, oh, when they mean tours, they mean all these other possible things, and probably even, other things. And then it's going to stuff about me. I might want to go hiking. I like Indian food. I heard yesterday about bunny chow, right? If you're the South African Indian food, the item to eat is bunny chow. If you're not from here and you want Indian food, apparently this is what you want. So I was told I have to go now tonight and try bunny chow, which is curry in a bread bowl, but better than that. So I actually can't wait, right? So this is good. And that actually, even if I did that query now on certain things on my phone, it would say, wait a minute, I'm connected on social media with Nick and Doug and Ben, and they are close to me. Okay? So Facebook, you ever had a creepy experience? I don't know if you use Facebook, Instagram, any of that kind of stuff. You know, they sometimes seem creepy. Like, why are they? You know, I just mentioned 2 minutes ago bunny chow, and the phone's going to go, hey, here's a great place to go try this, right? South African Indian food, right? That's because, you know, it does know. It knows Ben's here. It knows I'm connected with Ben. And so it's going to say, well, what do they share in common? You know, what kind of, you know, he's probably going to want to do something with, I mean, Ben's not going to want to do things with me, but, you know, whatever, right? So the sort of eeriness comes from the fact that, hey, we're all telling Facebook that we're here, and Facebook goes, oh, look, they know each other, right? And then also Facebook will go, oh, wait a minute, you know, Ben knows Maria there, right, on Facebook. Why? I'll start recommending that I friend her because we're all in the same room together, so maybe we all know each other, right? Okay, so all this stuff goes in for the query, okay, and that goes in, all gets stuffed in right at the bottom of that vault. It's all shoved in there, right at the lowest level, all that information. And all that is something that's expressible in a query that can be solved with an inverted index, okay? That's the very low level of what happens here, okay? So then we go up the volcano, okay? And at the lowest level, we still primarily depend on the fast matching. So there's a whole database kind of technology in doing the fast matching of all these characteristics against an inverted index with some help from geolocation and stuff like that. And if we go back to that data center I showed you at the beginning, that search will not take place on one machine. What you do in the lab today is something that happens on one machine. That search actually, because there's so much data, that data is spread over a large number of machines, hundreds, okay, and they all index part of the collection. So that search gets handled by a bunch of those machines, and then that will get hundreds of thousands of items, hundreds or thousands, depends on the query, depends on the environment, might even be hundreds of thousands, okay, and that goes up to another thing that will now start to use more and more machine learning to figure out what the answer is. So at the lowest level, you get a very simple, relatively simple database technology that searches an inverted index very fast. Okay, there are algorithms that do these things extremely quickly, get you a pool of things, and now as it comes up the volcano, you get the lava gets smaller and smaller and more focused, and we do more and more machine learning on this, right? So at the lowest level, we have some kind of TF-IDF thing, and then as we go farther up with some quality and a bunch of other things, and then as we go up, we start to depend more and more on machine learning and learned rankers, okay? And I'm going to just give some very, so I got what, another, can I go to 20 after? Yeah, I think I'm supposed to end at 10 after, but I started a little bit, sorry, 15 minutes after, right? But 20 after is good, right? Okay, so I'm just going to give little tastes of machine learning now as it applies to search, but then the idea, I think, of the sort of information retrieval component of the week is at the end of the week, Nick and Bhaskara will spend a day talking about, so one of the things that happened on Friday is neural rankers, modern deep learning methods applied to this. So, and I think you guys, you told me, Bhaskara, you're going to do a little bit of classic, like Lambda Mart and stuff like that as well. Is that? Lambda rank, okay, yeah. Some one of those kind of, I'm going to do Lambda Mart here, actually, a little bit of it. Okay, so what happens then, we have tens of thousands, let's say tens of thousands of documents that have come up from the volcano. So these are things that are a pretty good match textually and conceptually with South Africa and tours and tourism and stuff like that. But there's still tens of thousands of these documents. So now we're going to build a learned ranker. And classically then, we'd have a bunch of features. Sizes of the documents, global statistics, spam scores, and readability scores. If you've heard of Google PageRank, That will be in here, although PageRank, the way that it was presented 20 years ago, that you might have seen written up somewhere or read about in a paper or heard somewhere else, that's kind of not quite how it works anymore. But it's still an interesting algorithm. A lot of other quality indicators, location, all these derived features. So BM25 and IDF features will come as features into the machine learning algorithms. And whatever you think of, there could be thousands of these features related to the count of friends in the room or the number of times I've been here. Anything you can think of can be a feature in these learned rankers. And these then are turned into very long vectors of numbers that have been normalized in various ways. And this is the raw material then to do machine learning for rankers. So, boy, I'm way behind. Okay, way behind. Okay, so machine learning needs lots of training data, which means lots and lots of query item combinations. And basically, what we do, depending on the ranker, is you say, okay, this is good, this is bad, right? For this query, this item is good or bad. You can also say things like, for this query, this item is better than that item, right? Or you can say, for this query, this is how you should rank these items. Okay, and this is the kind of training data that goes into the machine. So any machine learning algorithm in the world is going to need just tremendous amounts of training data. So for search, we have a special problem, is where we get that training data. And it actually turns out to be one of the core things about search and recommendation. A lot of what I'm saying here is about recommendation too, is getting training data for these sorts of things is actually quite hard, okay? Not saying that other areas are easier, but if you're, for example, doing image recognition, you have a picture, somebody says, yes, that's a picture of a duck, okay? The problem with search is that it's very hard to figure out what the right answer is, because you have billions of things that could be the right answer. So to some extent, to label the data and say, oh, for this query, this is the right answer, you have to find this answer, and in order to find the answer, you have to have a search engine. So there's some circularity here that we'll come back to. Okay? All right, so we'll come back to that. So I'm going to look at a fairly old ranker, and I'm only going to look at it very briefly so you can get the idea. So we have basically training data, and the training data will look like, okay, no chalk. The training data will look like, here is a vector that represents an item. Here, don't worry about it. Here, the moment has passed. Here's a vector. Here's a vector that represents an item in the collection. Here is a query, okay, and here is another item. And basically, we know one is better than the other. And so, for learning to rank models, we want to minimize some kind of cost function that often reflects the fact that the ranker flip things. So there's a penalty for flipping them. And what you want to do is minimize this cost function to reduce the number of these flips and also how important the flips are. Okay? So if we're way down in the ranking and we move something from 35th that should be at 35th, right, to 34th, and you flip that around between 34 and 35, that's not very important. If you're way at the top and the number 1 thing goes to number 3 and the number 3 thing goes to number 1, that's a heavy cost. So you want to penalize your ranker a lot for that. And then a lot of these things tend to work with ensembles of regression trees. This is a very famous one, but there's lots of variations on this. GBTs and things that are used for actually building these models. But the important thing to get out of this slide is that for machine learning, we need to minimize the cost function, and for ranking, it's often got to do with how you've changed the rankings. Have you changed them in from the ideal, right, from what we're after? Once again, this will come back on Friday. I'm just okay. Okay, so where do we get this training data? And it's from a combination of online and offline sources. So one way to get training data for machine learning is to let people use your search engine. And then when they enter some query, Cape Town tours, what made them happy? That's what you want. You label, say, the thing that made them happy, that's the thing they wanted. How do we know what made them happy? I will come back to that. We also do it offline. And you actually have to do both. I mean, if you're running a commercial search engine, if you're running Google, if you're running Bing, if you're running Facebook search, if you're running Amazon search, if you're running any of these things, then you're going to have both of these components, right? Because they sort of are guardrails in some ways for each other, right? If you just train on online data, what you get is you get stuff that people click on because maybe they don't know what it is, or the thing is, if you are running a search engine and you respond, and you just want to count the clicks you get. Here's how you get your click count up. You get a video of a bunny rabbit eating a banana. And a bunny rabbit eating a banana is the cutest thing in the world. Just search bunny rabbit eating banana, and it's so cute. And just put it in the second result for any random query you like. And people will go there to Cape Town tours and they go, oh, what's that? Oh, look, it's a cute video of a bunny eating a banana. Why it's in your search results, I don't know, but people will click on it and they'll watch it. And if you have to tell your boss you got more clicks, that's how you do it. Okay? So you need to have and this is a real thing. You can really do this. You can put this bunny video in and get more clicks because it's cute. Nobody's going to say, oh, I don't like this. They'll just go, why is I search for Cape Town tours? I guess the bunny was on a tour. Anyway, try it. It's just, they're so cute. Bunnies love bananas, right? You know, I don't know why they don't grow in the same place. But anyway, the other thing you can do is you can ask people. You can say, okay, Cape Town tours, here's a picture of a bunny eating a banana. Is this a good match? And they'll go, oh, that's so cute. No. Okay. So we have to have their guardrails for each other. On the other hand, it's very hard to do things like personalization by asking other people to label the queries. So you need some combination of these things. Okay. So if we are evaluating machine learning rankers, then we want to know, is our search engine returning the stuff that makes people happy, right? And then how can we make it better? And if we think we made it better, how do we know? And these are basically two sides of the same coin, right? So evaluation and training. So we want to get labeled training data to label our rankers, and we want to get labeled data to evaluate the quality of our rankers. And these are two different but exactly the same things. So the approach to getting the labeled data for training, for machine learning, and the approach to getting data for evaluation are almost the same. And practically at this point they are the same, like in terms of what I'm saying here today. And then also for both of them, there's online and offline. And the question online is, do the results, are they making people happy? Whatever that means. And do they look good? Whatever that means. Okay, so there's really four things here: training, evaluation, online, offline. Okay? I'm talking a lot. I got 128 slides to go through this morning, and we're on number 35, so I'm just I'm probably going to stop earlier than I expected, and then I got another hour and 15 minutes after this. So you had a question?
I'm just taking a typical example of marketing.
Yep.
How do we evaluate or understand that something is not too rigged in terms of, for example, we can have a system by which the bots can keep on querying different things and then it can open up different things. How do we actually evaluate that something is, from marketing point of view, anything can be rigged, or from election point of view?
Right.
How do we evaluate
So I'm not gonna talk about marketing or elections because I don't actually do those things. I do commercials. I do search, which has a similar problem. And the problem he's really talking about, I think, is about things like bots or people hired to do these things. And so I said in some environments like the web, it's adversarial, right? People have spam, they have link farms, they have people hired to click, they have bots that try to do everything from very simplistic things to very complicated things. They have automatic programs that enter. I mean, the reality is, you see this, right? People will enter, you'll see queries, long strings of queries from different places with some politician's name, and then, you know, surprisingly, this person, you know, enters a politician's name and then immediately kicks on the second result, and then enters and does it, and then different people are doing exactly the same thing, and you go like, yeah, we see that. Right? So yes, it's very hard. You have to be aware of this, but anybody running a commercial search service knows this, and there is a team inside that is fighting the people on the outside, right? And sometimes the things that people do are very easy to spot, and sometimes they're very hard to spot. But yeah, this is a big thing, which I won't talk about, but it's definitely like any commercial search service is basically going to have a team that is trying to be adversarial and remove the signals that don't really mean anything, right? Which is why you have offline, right? Because that also helps, right? You know, replace a video of a bunny eating a banana with a politician. It's the same thing, right? If you see all these clicks, you'll push that politician up unless you know that you're not, you know, these aren't real, right? Okay, and that's actually coming to exactly why it's hard to do evaluation. It's hard to know whether your search engine is working, and it's hard to get label data because it's hard to know what the right answer is, right? Unlike a lot of machine learning problems, search recommendation has this tremendous difficulty that we don't know what the right answer is for a bunch of reasons. I type Cape Town tours, okay? I might mean a specific business called Cape Town Tours. And if you don't know there's a specific business called Cape Town Tours, you showing me the TripAdvisor page for Cape Town is the right answer. But I'm going, no, I don't want that. I want the company called Cape Town Tours in Canada, right? Because, you know, there's Nova Scotia has capes, right? You know, so it's very, very hard. And, you know, it's very circular, right? We need some kind of search to know how to find that right answer, and we need to, you know the right answer to build a search engine, right? So we have to get the search engine to build its own labels, and that requires basically a whole continuous optimization loop where we look at people, what they're doing, we build models. Either these people can either be people that are hired to label data or real people using your system. You need to know, this is kind of interesting. I said, make people happy. Well, there's a whole machine learning problem in looking at what people do with your search engine and deciding whether you made them happy or not, whether the label you should give to what they clicked on is yes or no. Okay, and I'll come back to that this afternoon, I think, in the second lecture. And then we basically optimize our system and build a better user experience. So there's a kind of a positive feedback loop here. I'm going to talk about offline evaluation for a bit. But is this a good place to stop? Yeah, okay, why don't I stop? How long is the coffee break? 50, so just till 10:35. All right, 10:35, 15 minutes. We come back. All right, I'm going to stay here. I'm going to get a drink, but I'll hang out here if you want to ask questions. And I clearly need to speed up just a little bit, but we'll be okay. We'll be okay. All right, so 10:35. We'll see you back here.
Doki is going to search around.
sometimes I check those scrap.
Let me just find him myself.
I might still have these in
Thanks
different
to that, it's really the lyric features out of it. But actually, let's say maybe not do the full recognition, but just. Let's pretend. That's just a mix Actually, for lyrics, you don't even want exact message. You want I did get peace of mind. So actually, I didn't try both, but like what I did do is, any company, I did kind of make sure that there was a search engine. But there's no eBay here. Which might actually, which is not owned by that. That's what I was going to say. Quarter to. Okay. Okay, I'm gonna keep going, and 12 o'clock, 5 minutes after 12, lunch will be served. So we got a voyage of 1 hour and 20 minutes or something. Okay, so I said there's offline and online. So online evaluation or training data, either one or the other, is to look at how people behave with your search engine and in some ways try to interpret the behavior, and I will come back to that. And then offline evaluation or training, so you're either figuring out whether your search engine worked or getting labeled training data. They're very close, they're more or less exactly the same thing. So we're doing evaluation. This is the tool set you need, and you will do this afternoon. You need a set of queries. It will be thousands for commercial search. It'll probably be dozens. So 50 is a typical number for some machine learning and research so only a small number because the labels take so much work to generate. And then you need some search results, and we want to find out how good search our results. And we ask humans basically questions about relevance. So is the item you found relevant to the query? And you often do a graded scale like this that goes all the way down to harmful, and we will talk about that. I say in the second lecture, this is already the second lecture, so we'll talk about it in this lecture if I get to it. So here's an example I had from Facebook to show you actually how difficult it is to say what is the right answer. Here we actually have pretty good right answers, but if I type Trump into Facebook at that time, we have two things here. And these are both the official accounts of the President of the United States. You can tell they're official accounts because you see that little blue tick mark that says it's been verified. So this is a quality signal that says it's really good. And the question is, which of these is the best result? This one, which is the President Trump as a government official, or this one here, which is Trump as an individual. Okay? If I put them side by side, okay, someone type Trump, government official, public figure. Which of these is better? There is a correct answer. Okay? They're both, a human would label both of them as perfect. Right? So somebody who's more familiar with US politics, Doug, which is a better result for Trump? The one on the right here. Why is that? Yeah, this is the one, and if this was Twitter, this is the one that the President of the US tweets out on Twitter all kinds of interesting things. And So this is the more interesting account. Actually, here's a clue. This is only 2 million people like this, but 23 million people like that one. And in the context of social media, you see that some of the people that I'm friends with like this page as well. So in a more academic environment, export controls cryptography. This is an old query from a test collection from a group called Trek, which we'll probably come back to. And what happens is we just label these as relevant or non-relevant. So a person comes in and says the first result is not relevant or the second result is relevant. Okay? So that's the kind of labels. So once we have these labels, okay, evaluation, we use any number of measures that say, okay, we have a ranked result, we have a bunch of labels, how good overall is the ranked result? And we'll look at a measure today called normalized discounted cumulative gain. I'd say in the second lecture, but that means now in a minute, okay? So I'll come back to that, and you will use that measure in the lab. Okay. And on Wednesday, one of the talks on Wednesday is called The Role of Evaluation for Search. So Nicola up there, never mind. The people over there are going to give that lecture. Okay, so let's do online evaluation. Online evaluation, I said there's two parts, online, offline. Online, we want to guess whether the person is happy. And you were asking me about this earlier, okay? So this is the part of the lecture just for you. Well, them too, but you and you. So for online evaluation, the basic signal is a click. But the real question is, so somebody's typed a search, Cape Town Tours, and they clicked on it, and that is your very clear signal of something. And the trouble is, we really don't know what it's a clear signal of. Okay, and there's other signals. I'm going to spend some time talking about clicks because people who work in search, especially if you work for a large search company, they understand all this stuff. But if you work for a relatively small place, you've got a boss, right? And the boss, they want you to do something. They pay. You're very expensive. You're a machine learning engineer. You cost a lot of money. They want you to prove your worth. They want you to prove that you can make their search system, their recommendation system, better, okay? If they're selling a product, you can always use money, right? But if you're not selling a product or not directly selling a product, then people look at clicks. And if it's the end of your evaluation period and you're going to be reviewed and you need to get clicks up, remember to queue money. Just put it into some search results, you'll get your clicks up, no problem. It's the most useful thing I told you all day is if you need to get your click rate up quickly, put a picture of a cute bunny in. There are other signals as well, which we're not going to spend a lot of time on, but what happens if someone runs a query and just walks away from it? You don't get a click at all. That could be bad, unless you just showed them the answer they were looking for, right? What is the temperature in Cape Town? For I can tell down here it's about 15 degrees, but I think it's a little warmer up there, right? They look at the result, they see 15 degrees, they walk away, that's fine. On the other hand, if it's something else, then maybe no click at all is bad. How long they spend looking at results and pages linked from the results. This is a very important thing. If they change the query, that often means that it's bad, that they didn't see what they were looking for. And so they had to change their query to make it better. But it might also mean that they saw what they were looking for and said, oh, what I really want is this other thing, right? So it might be good, it might be bad. It's very, very hard to tell. There's a lot of very, very complex signals we can look at, but I'm going to start talking about the clicks just so that, okay? Here's another real page. So someone typed Disney, and then they typed click there, right? So Disney, there's the company, there's like Disney Entertainment, there's some groups for fans, and they clicked here on the Wikipedia. Okay, so what does this mean? It could mean that they found what they're looking for. Well, what does it mean if they come immediately back? They click on the Wikipedia page and then they immediately come back. They say, oh, they hit the back button. What does that mean? Sorry? I can't tell who's talking.
That means it's not what they want.
Yeah, probably, right? They clicked on it. Maybe they clicked by accident, right? They got their thumb on the phone, right? So that's that kind of quick back signal. You know, clicking on something is good, but coming back immediately is usually bad. And if they stay on the page for a long time, probably means the opposite. Yeah. Oh, I'm sorry. So that whole part of my talk will not be properly recorded. I apologize for that. Thank you for reminding me. Okay. I said I don't really need the microphone. You can probably hear me worse now because I got the microphone on. Okay. All right. And another signal is if the first two are clicked. Now, do they mean that those things are bad for that query? They probably mean that for this person, that's not what they were looking for. Okay, or it could just mean that they hit the thing by accident with their thumb. Okay, this is the kind of thing that we have to try to understand if we're going to learn from online behavior. So interpreting clicks is very hard. There's a bunch of things. A click might be good because they found what they're looking for, and it might be bad because they are bored or they couldn't figure it out, right? The longer the time is usually good unless they found what they were looking for quickly and came back, or they're very confused. Maybe they are on something for a long time because they're trying to understand how they got on the Wikipedia page, right? And skipping results are usually a bad indicator, but they just might mean that's not what the user was looking for, right? So if you work, especially if you work for a company that hasn't done a lot of search, your boss thinks it's a very simple thing. You just count the clicks, okay? But it's actually very, very hard, okay? I think I'm taking a long time because I have to walk back here. So interpreting clicks is very hard, okay? There's some things that are our friends, right? The lower down the ranking people click, that's usually more of a good sign because they had to go all the way down there. So if they click down there and then click these other things, this is probably the right answer. And then the other thing is that the things probably that weren't clicked, averaged out over lots of clicks, probably aren't the right answer, right? One of the things we can do understanding what the position of the click means is to randomize some of the queries and give them just back, okay, instead of 1 to 10, you just scramble them up and see which ones they click on. That kind of annoys people, but it's a powerful source of insights. Okay, so let's go back to click rate, okay? Here's what people usually mean by SERP, means search engine result page, sorry, yeah, it says that up there. Okay, so the click rate is usually, let's say, this is one definition, the number, so someone runs a search, they click on it, that counts here in the numerator, and the number of searches they run counts in the denominator. So this is, if your boss is thinking about how to measure how good your search engine is, this is probably what they're thinking about. Okay? But you want to be very, very cautious of this. This is a trap of badness. Okay? This is the hardest thing to get right for online search behavior, right? And I'll come back to this. I just want to plow ahead a little bit into A/B testing first, and I'll come back. Okay, so I got a click rate. I got a SERP click rate. I'll come back to why it's bad in a minute, but it's our measure. That's what the boss says. The boss says, get your click rate up. And I already told you my trick about the cute bunny video. So, if you're right down to the wire and you got to get it up, do the cute bunny video, okay? But we have a measure. We have our click rate. And we want to know if something we did to the search engine made the measure better. Okay, we added the cute bunny videos. We had better training data for our ranker. We had a new ranker. We introduced a neural network. Right? Everybody wants, we need to have a neural network in our search engine. You put one in, how do you know it made it better? Okay? So we're going to do A/B testing. People here probably have done A/B testing if you worked in industry, right? We're going to do A/B testing. So we split sometimes control and test, okay? And we have the original system and we have an experimental system, and this will, you can use this for a lot of different kinds of things, right? You can use it for UI changes, you can use it for machine learning changes, things like that. So lots of different stuff. So A/B testing, though, is kind of tricky. So here's A/B testing. We got A. Okay, this is before. This is our improvement. Which of these is better? This is a trick question. We don't know. Okay? We had 2 machine learning algorithms. One produced this, one produced that. Which is better? We got to go to millions of users and decide which is the better situation. Okay? Okay. So what we're going to do is we're going to take our change and we're going to partition the query stream from all millions of people, billions of people using our system. We're going to partition it into 2 pieces, the people that get A and the people that get B. And I'm going to make a distinction here based on experience where we're going to have 2 kinds of ranking of changes. Changes to the ranker, so changes to the machine learning algorithm. This means that the user only just sees different results. They don't see them presented differently. Okay, there's no UI change. It's just the result that used to be at 2 is now at 1, or the result that used to be at 10 is now at 1, or the result that was never there is now at 1. Right? Something got better. Okay. Right. Comparing a real-time web crawler, so updated the index faster to something that used a batch crawler. So we want to see, is the fresher data better? Anything that's not changing how the user sees it, that's a ranking change. On the other hand, we have a user interface change, okay, and that's where we have maybe a new way of presenting the results or a new way of laying them out. Maybe instead of like this, we're going to lay them out like that, okay? So for user interface changes, we don't want to switch back and forth between interfaces for a user. We basically take the user and we always say, are they control, are they test? So each user in the world will either see the new way of doing it or the old way of doing it. And then we can compare the click rates, say, on those 2 things, and we say, oh, this is better, right? And we adopt a new change and you get a bonus, or it's not better, you made it worse, so you lose your job. Okay, so very important there. Okay. And though for ranking changes, it's actually useful to do it by query. Okay, it's a little bit more complicated than this, but I'll simplify it this way, so that I enter one query, I see the old ranker, I enter a different query, I see the new ranker. And the reason I want to do that then is I got people that I can then I can do within user experiments, right? So it increases the sensitivity, right? There are more queries than there are users, and so I can do my A/B testing, I can smear it out across all my users, right? So I somehow take the user ID and the query, hash them together, and decide then whether to do control or test. Okay. All right. So I've run an A/B test, and you have to run these things sometimes for a long time, maybe a week, maybe 2 weeks, right? To see statistically the effect of what you've done. For one thing, the kind of changes you've made to your machine learning algorithm may only impact a small percentage of the queries, right? Maybe the changes are, very subtle, whatever. You still want to show, even to show, even showing half or a tenth of 1% of a change is actually a major change when you have millions and millions of people using your search engine, right? So small change, you're not getting a 1% improvement in click rate is wow. Okay, getting like more than that is amazing. Usually you get, 1% over a subset of the queries you're really interested in. So any kind of change A/B test will take a long time. It might take a week or more. And so we have our signal, and we want to know, I'm not going to talk about statistics, that's another thing, I just want to know how we know that things got better. And I said, okay, we'll go click rate. Okay, the trouble with the click rate is that it's actually a very, very broken, I'll come back to why. It's a very broken metric. Okay, what we really want to do actually is we want to have a whole bunch of metrics, right? So we want, right at the top of we want a hierarchy. If you're measuring search engines, you're measuring recommendation engines, you're measuring anything online. If you're measuring anything online, this is true, selling stuff, anything else, you'll have a top line metric that's very, very robust and has very few assumptions, but it's hard to move. So conversion rates in selling things, right? Actually getting, I have queries per user here, but actually increasing the number of daily users of your search engine, right? People are coming back, right? Those kinds of things. Those are really strong. So in social media, if people like posts or they make friend requests or they follow people, any of those kinds of really strong things, those are very clear signals of success. And those are the long-term signals that you really want to track to say things are getting better over time. But they're very hard to move. And then there are sort of session level metrics. These are, I come, okay, I type Cape Town tours, then I look at some things and I come back and I type another query, and then I look at some things and come back and look at another. So over that session, what we can do is we can actually build a machine learning model to say, was the person happy with their overall experience? Okay, did they find what they were ultimately looking for? Right, and those are more sensitive, okay, and not as robust. You might need to build a machine learning algorithm to say whether the person who did these sequence of searches were happy at the end, but they're a little easier to move than these top line metrics. And then these very low level metrics, click rate, dwell time, things like this, they're very easy to move so you can impress your boss, but they're broken in a lot of different ways. Okay. So, in particular, you want to watch for movement. Ratio metrics are a bad idea. Okay? Any metric where it's click rate is a bad idea. Because let's pretend I made a really great improvement to the search engine. So people use it more often. But they use it for harder things. So you've made it great. You've made it work really, really well, right? Right? So it's the number of clicks over the number of searches, a numerator over a denominator, okay? So what you've done, people use the search engine way more, so you've made the denominator bigger. But because they're coming with harder, so for the easy queries, they find everything really fast, but they're coming with harder queries. So the number of things they click on goes up because there's more stuff, but because they're harder queries, it doesn't go up as fast as the denominator. So even though more people are using it more often, the rate has gone down. Okay, whereas I looked at the two pieces individually, I'd see the clicks going up and the usage going up, and I'd go like, wow, this is great. Whereas all I looked at was the ratio would be going down. It's like, wow, I thought I made it better, but it's getting worse. Okay? So if you can change the number of SERPs, you can change this in counterintuitive ways. Reformulation is another factor. If you can reduce the number of reformulations, that's good, but that also, that can also sort of change the denominator versus the numerator in very strange ways. And then you have to be very, very careful. You have to be very, very careful with your ranking engineer, well, not your ranking engineers, with your logging people. If you say that you're measuring SERP click rate, right, search engine result page click rate, and people are clicking here on the related elements, is that a click on the SERP? Right? I'm measuring click rate. People run a query, they get the results back, they click, number of queries they run, number of queries they click on, one divided by the other. Does this count? Does it count in the numerator or the denominator? Okay? So your logger, the person who's writing your logging code, thinks this counts in the numerator. right? Ran a query, I clicked on the results, but this means I couldn't find what I was looking for because I'm changing the query. So this counts in the denominator, okay? And so if you don't pay attention to your logging code, right, you'll end up with, well, you'll end up looking good because you've decreased the number of happy people, but they're clicking on the page more trying to find the right thing, right? So you have to be very careful with these metrics. All right, that's enough about that. Any questions about that? Because you asked about that. It's actually, interpreting online metrics is like a crazy hard problem that, sorry.
Yes, I was wondering that you're talking about treatment of text, most especially using the WordNet,
Yep.
which is the lexical database for English language.
Yep.
So I was wondering if there's a provision for social media languages.
So other languages other than English is, yeah, so if you're talking about WordNet, you're sort of talking about query kind of understanding and indexing. And so in a sort of, now actually there's a lot of tools that work in a broader set of more common languages. But actually a real problem is, what do we do with less languages that have fewer resources, that don't have these tools like WordNet? And actually I think Doug is going to talk a little bit about that this afternoon as well. So actually we're going to have a little bit of a session devoted to how to get some of these tools like WordNet available in less common languages, okay? I think that's your lecture, right? Is the, more or less, low resource languages, yeah. Okay, so I did the basics of search a little earlier. Okay, many things I left out. I will allude to some of them. One thing that you'll see that's actually tremendously important, so I went to Bing, I typed Cape Town tours, and it immediately suggested a bunch of these queries like this. And I'm not going to get into where this comes from. This is a whole other really interesting area. I mean, this is another bunch of machine learning in search, and a lot of this is learning from the past searches, learning from what people have done in the past, right? And like the answer to Cape Town Tours probably is Cape Town Tours TripAdvisor, and so this is the kind of thing we're not going to get into today, but is actually in and of itself an interesting part of machine learning for search. Okay, and when we get to the top of the volcano, there's a whole bunch of other things in putting together a page like this. There's a map, there's some images, there's a Wikipedia result, there's all the things that come back from different parts of the ranker, there's some ads in here, and a lot of these things are whole teams. Like here's an example of something that's been popped in there that says 3-day Cape Town, I can't really read it, okay? Table Mountain, you can't read it, and cable car, okay? So this has been there's a whole team at, I guess I got this off of Bing, I'm guessing a whole team at working for Bing that just built this thing here, and a lot of the stuff we'll talk about, ranking, machine learning for ranking, all this kind of thing, in building these special modules that drop in like this, all of the same kinds of basic technology is going to be used, right? Diversity is kind of interesting. Diversity means we interpret queries in different ways, and it sort of competes with this idea of consistency, which is to figure out the dominant interpretation of a query, go with that, and then give a way to people to click on alternatives, okay? So that's the end of me talking about commercial search a lot, and I really want to now just go for the next 50 minutes or so, talk about research. So I'm back in academia now, I'm not in industry anymore. How do we do research on search technologies in industry? And there's going to be a lot about machine learning this week, so I actually will give a sort of contrasting thing. But the question is in a university, how can you do the science? And what is it you're going to do? And here's really the role of research, right? If you're a ranking engineer working at a company, your problem works like this. You're working in search recommendation, you get a problem, and then you get a few weeks or days later, you're shipping code and you're done. So you solve the problem, you're finished. You go on to the next problem. If you're an IR researcher, you're doing research in information retrieval, you have a problem and you write a paper, and that takes months, and then you take the same problem and you write another paper, and you keep writing papers until years later, you have your PhD, or you have tenure, or you retire, or whatever. So you get to spend a lot of time thinking very carefully about how problems need to be solved, right? And what the ranking engineer, what the person at Facebook or Google or whatever want out of you is they want a cookbook, right? They have their specific problem, and they want to go and say, what is the right machine learning algorithm, what is the right user interface technique, whatever, to solve that problem, right? So we do need fundamental research here. We need to understand search technologies, interfaces better, how people work with complex tasks, and we need better machine learning, okay? So here, this is where I'll speed up a little bit. Here's some problems I'm sort of myself personally working on. I'm going to give an example in a minute. That was supposed to be the end of the coffee break, okay? So, all right. So let's talk a little bit about this volcano in a research environment for a second. So at the bottom level, we are still doing some kind of TF-IDF ranking, okay? And research down there, a lot of it has to do with efficiency, has to do with building better index structures, building faster mechanisms for search, building more expressive queries, bringing in entities, doing entity retrieval, graph retrieval, all kinds of things that at almost database level that make search better. And moving up, you know, there's machine learning for search, right? Learning better mechanisms for learning to rank, for machine learning for search, right? And then moving up the volcano farther are mechanisms for improving the quality and consistency of search results. So how do we, if I issue a query, how do I make the results more consistent? How do I make them more diverse? How do I make them not repetitive? I think one of the examples you'll see we give you a few test queries around in the lab. I think you'll see some of them produce very repetitive answers. So how do we reduce the repetition? And then at the very top, it's HCI, right? So search is in recommendation. Almost everything I'm saying here applies to recommendation, but I mostly work in search, so I'm doing that. Everything touches, you know, down here, the research is almost like database research. I work with database people, right? And here, the research tends to be very much machine learning oriented, and at the top, it's HCI, human-computer interfaces. Okay, and so the research spreads all across this. And I'm going to have some concrete examples at multiple levels here. Okay, so we do all this kind of stuff. So what I really want to do, now I'm going to go into, I wrote a paper mode, and I'm going to do this as an example of the top of the volcano, which is how do we present search results? How do we have an impact on search results that is beyond what necessarily you might see being done in a commercial environment? Okay, so this is a single thing, and it's something we did lately at my lab, and a PhD student did this. And the question is, how can a search engine do harm? How can it hurt people? Okay? And this is on the human-computer interaction side of things. I'll come back to the machine learning part in a minute. And so we have, how can a search engine harm people? So here's the thing. You know, you have a family member, a loved one, and they're very sick. And the doctors, they don't know what to do. So you heard something that is this Hoxsey treatment, which is amazing thing. So you go to a search engine and you look that up, and here's sort of the results you might get back. Okay, these are real results, but I won't say when and from who. They don't necessarily look like this. So here's a bunch of results from actually typing that query in somewhere, okay? And we have something that says, hey, here's the clinic that offers it. Here's something that says the method is not scientifically proven to be effective. Here's another place you can get the treatment. Here's another place you can get the treatment. Here's an article endorsing it, and it says, look, I was skeptical, but I was converted. And here's a Wikipedia page. I think this was the Wikipedia page that says it's not effective. And here's another success story. So the question is, does it work? The answer is absolutely not. That is medically based. There is no medical evidence whatsoever. You will waste your money and you will not get better. Okay? And this is where people really get health information. So if we don't get this right, okay, we can really hurt people. All right? So how are people influenced by search results? Well, this is what we did. We built a fake search engine, and we got a number of possible treatments for things, some of which sound weird, but actually do work. There's medical evidence that they work. Then there's other ones that are also strange, and there's medical evidence that they absolutely don't work, and some where medical evidence is inconclusive. Okay? And what we did is we showed them fake search engine results. So sometimes most of the results contained incorrect information, right? Okay? Sometimes the majority of results contain correct information, and we played around with the ranks and things, and we asked people, you know, do they think, after looking at these search engine results, do they think the treatment helps or does not help? Okay? And all of the questions were, does X help Y, right? And there's something called Cochrane Review that supplied whether it was helpful or not. And here are some examples, right? Do insoles help back pain? Okay? I think the answer is no. Do probiotics help treat eczema? I think the answer is no. Does caffeine help asthma? I think the answer is yes, actually. And does surgery help obesity? Well, yes, as long as it's the right kind of surgery. If you're having your tonsils taken out, that doesn't help obesity, except for you get to eat ice cream a lot or something. Okay, so we told people that they were pretending to be searching for an answer to a question, and you had to say, is it helpful, inconclusive, or unhelpful? And we manipulated the searches they saw. We also had a control where we just asked them. We didn't give them any search results, and we had an interface that looked something like this. Okay, and we manipulated the results. Sometimes we showed them always an 8-to-2 ratio, sometimes 8 correct and 2 incorrect, sometimes 2 correct, 8 incorrect. And we also manipulated where was the first correct answer, at rank 3 or rank 1, okay, and the rest were placed randomly. And we had 2 measures. One was accuracy, so that was the fraction of correct decisions. Remember, I said in metrics, you want more than one metric. So we had accuracy, which is the number of correct decisions, and the harm, which was the fractional harmful decisions. Okay, so this is a little bit different than how you normally evaluate search engines, where harmful decision is the opposite of the truth. Okay, so you say it helps when it doesn't help, or vice versa. And both of them are harmful, because if something helps and you think it doesn't, you missed a chance to get better. And if you think something helps and it doesn't, then, well, insoles are not going to, but they're going to be uncomfortable, but other things can be genuinely harmful. So what we found is that, and this is in the lab, so these are people that know they are under some kind of experiment, okay? This is not in the wild, but even in the lab, if you bias the results toward incorrect information, accuracy dropped now. So it says 43%, but remember there are 3 possible choices. So a random choice would give you 33 1/3, right? So incorrect information dropped accuracy from 43% to 23%, and toward correct information increased their accuracy. And I won't get into all of the findings, but basically the outcome was that so with control, no search results, people could guess the right answer more often than random. But if you showed them the correct information, then they got a lot better. But if you showed them incorrect information, they got a lot worse. Right? And in terms of harm, once again, harmful results not often. Showed them correct stuff, harmful results hardly at all. But if you showed them incorrect, mostly incorrect stuff, that would cause harm way more than average, way more than random. We followed up with a think aloud study. So we had them do questionnaires, eye tracking, video, everything else. And we found that the prevalence of an answer, so people, the odd thing, people tend to look at a page of search results and think it's some kind of vote, right? So if 8 out of 10 say yes, people think, oh, that must be the answer. If 8 out of 10 say no, people go, oh, that can't be the answer, right? They're also influenced by things like quality. If something seemed authoritative, like a medical study or something like that, they would mention that, okay? So this is where I save time. People saying things about prevalence, people saying things about authoritativeness, people saying things about quality, people saying things about did they believe the earlier results, okay? So what the whole study came down to was really proving, or not proving, but demonstrating that you can cause harm with a search engine if you're not handling the results the right way. If you're telling people, and the result, these are all relevant in the sense of these are all pages about the thing the search people were looking for, right? These weren't things that you look at and go, well, that's got nothing to do with my query. These were just things that had everything to do with your query, but were telling you the wrong thing, usually for commercial reasons, okay? And I put that in as an example because a lot of people think these technologies are all about ranking. It's all about machine learning, but they're all also about the interface. They're all about how you present the results to people, right? And what impact those results are going to have on people. Okay, and there's hundreds of examples. I use that one because that's something we did. A PhD student of mine just graduated with that. And I'm not going to talk. I had actually had some material about faster index structures, but I thought I cut that because I'm already way over. But we'll look now about improved machine learning for rankers and how we do that. Okay. So how do we improve rankers? There's a bunch of stuff coming up this week about this. Friday, they're going to do neural ranking models. And if you're not interested in neural ranking models, there's also Friday explainable AI, which is important from a search standpoint because a recommendation standpoint, because it's often good to tell people why you surfaced a certain result. Like, why did you give them this answer? I recommended this to you because you liked such and such, that kind of thing. And then another place we can do machine learning is prediction of user satisfaction. Okay, so we're working on this. So in a research environment, how do we know, how do we get the training data to train these rankers, and how do we know that they've done a better job? And there'll be more of this on Wednesday, but I'll do a little bit of it right now. Because you're going to be doing this in the lab. So the basic idea of how to evaluate and how to get training data for rankers goes back a long time, look, 1967, right? Okay, and basically you have some collection of items, documents, passages you'll see today, some queries and some labels, right, which indicate relevance, so not harm, but whether the document is related to the thing or not. And you basically you change your ranker, run these queries on your ranker, use these labels to see whether your ranker got better or worse, and this gives you a repeatable thing that you can rapidly tune or change your ranking strategies, right? And this is industry academia. This is what we call offline evaluation in industry, okay? And there's a bunch of places that you can sort of test what you're doing, okay? So around the world, there's lots of different research groups that work on common problems and tasks in machine learning for search. There's shared collection of documents, shared training data, common test data. Sometimes they have a leaderboard, right? And sometimes these things are called benchmarks or challenges. There's a bunch of them in academia. Okay, in the United States, there's been one since 1991 called TREC, the Text So this goes back to the point now they do all kinds of stuff, deep learning and question answering and medical stuff, but it was called the Text Retrieval Conference, TREC, right? And that's been going since 1991. In Europe, this used to stand for cross-language, what did this stand for? Cross-language lab for, no, that's what it stands for now. It used to be cross-language evaluation forum, but now it does so many things that this doesn't really mean anything. It means lab for something. So it's pronounced clay, by the way. It's a multilingual pun, and so you can look at it there. In Japan, they've had for a long time a similar thing, NDCIR, and in India they have a thing called FIRE that works a lot with problems that are local to India, but also problems that are broader than that. So these are academic groups. There are also industry initiatives. So Microsoft has this MS Marco collection, which is a collection of problems of data that you can use for natural language processing and search and a bunch of other things. It has a leaderboard there. So you'll be working with MS Marco today in the lab, the data that comes from MS Marco. Great. And was this your group that did?
We worked on it a bit, but that is the key question.
Oh, okay. All right. So the MS Marco people are around. I'm going to talk about TREC because it's the academic forum. So TREC, every year there are a bunch of problems that you can work on in machine learning related to search. 2019 had complex answer retrieval. That's going to go away this year. Conversational assistance, I spent a lot of time on that. Decision support, deep learning. So these are all the things people get together every year. They try to work on a common set of problems in these areas and get together in November in beautiful Gaithersburg, Maryland in the United States. But this happens in Japan and India and stuff as well. And work on common problems and create tools that we can use for later experimentation. And you will see, I'm giving you all this because you will see this in the lab, basically. So at TREC, there's usually a bunch of things called topics, which are not just queries, because they explain the information need and things like that. So one common problem is something that TREC calls ad hoc search. So this is just, you have a bunch of documents, you have a bunch of queries, you run the queries against the documents, you get a bunch of ranked lists, they evaluate the ranked lists and tell you how well they did. This year it was really focused on deep learning, but it's been running the same way with different kinds of technologies for a long time. What TREC does then is what happens is you have a bunch of queries and a bunch of documents, you build your ranker, you rank the documents according to the queries, you send your rankings into TREC, they make what they call pools, so they take the top 10 from everybody, they have a human label them, is this a good answer, is it a great answer, is it a bad answer, is it whatever, and they label the documents and they compute some evaluation measures and return the results back to the participants. And the TREC deep learning test this year, next year, is run this way. Here's an example of what they mean by a topic. So that part is the query. Okay, that's what you run. And this tells you a little bit about how the query is going to be judged. Okay, so in this case, the query is law enforcement dogs, but that is explaining what they're looking for. And here's an example of something that is, well, what do you think? If it's law enforcement dogs, this document, is that relevant? This is about picking up after your dog when it makes a mess. So, probably not. Okay. Another example that we did this year is they had a challenge or a task, which is to called conversational assistant, and what they gave you is a whole set of these conversations. So statistics and studying it for a career is the topic, that's not the query. What happens is, imagine you're talking to a device and you say, well, why is statistics important? So it comes back with an answer. So your machine learning algorithm has to come back with an answer. And then in the context of that first question, the second question is, why should one study it? And so your machine learning system has to do this co-reference resolution and understand that it means statistics, and then answer that question, right? And then it answers each of these questions in turn, and then once again these answers are evaluated by Trek, and you get a score. Okay. So here are some example answers. Okay, this one comes from Marco, which you'll work with today. This comes from a different collection. Okay, and there are two passages. And so which of these is, if the question is, why is statistics important? Okay, so you're the people that do the human labels, right? The question is, why is statistics important? Which is a better answer? Anyone want to volunteer? Probably the first one. Ben's done enough of this labeling, right? So here's a typical question for this, and so this is what the human labelers do. They look at these questions and say, okay, that one there's answers it completely. That's a good one. This is like, it's about statistics, so it's not completely wrong, but it's, it's just okay. Right? It's about a particular statistician. Okay. So they pooled it, label it, okay, and in this case probably the top one would be labeled ideal and the bottom would be labeled, it's not bad, it's just fair, or these are actually I think what the words they used, so that would probably be fair. The top one would probably be ideal and the bottom one would probably be fair. So what we have in the world, if we're doing research on how to build better rankers, we have test collections, which are documents, answers, other items that are going to be ranked, a bunch of queries, a bunch of relevance assessments. We generate a rank list. So you're doing this, you generate a rank list for each query. You'll do this in the lab. Okay, you generate a rank list for each query. And then you have these human labels, and you use this to generate a score. There's a whole bunch of these scores. We're going to see one called NDCG, and there's a tool for doing it called Retrieval. And the reason we want to use pretty much everyone using the same tool, so that if I report numbers and you report numbers, we know that the numbers mean the same thing and that you're better than me. Okay? All right. So NDCG, I think right. So the idea of these metrics are to translate human labels into a single number for each query that says how good the answer was for the question, or how good the ranked list was for the topic. And then we average over a whole bunch of topics. And the typical measures look something like this. So we sum over the ranks, all right? Some benefit from the thing at rank K, and then some weight that says, you can think of it as a user model. How likely is it someone to see the thing at rank 10? Or it's just a decay to say, putting, what you want out of these measures is you want to say something, a really great thing at rank 1 is much better than a really great thing at rank 6, right? And okay thing at rank 1 is better than a bad thing at rank 1. So we want to balance out these factors. So we're going to basically sum over ranks and say how good is the thing at the rank, and what's the discount for reaching that rank. Okay. So to get this discount, you need effectively a model of how a person might look at a ranked list, and you need to somehow take these human labels, good, bad, and turn them into a number. And there's a whole bunch of stuff about this, most of which is very people who are interested in this are interested, and most people are not exactly interested in it. But here's a ranked list. I think I might have stolen these slides from you, Nick, at some point. Yeah, I think they came from you to M&A to me, right? I was putting them together, realized, well, Nick's going to be in the room. He's going to go, hey, isn't that my slide from like 6 years ago? And the answer is yes. Thank you. Okay. So here's a query, black powder ammunition. Here's actually a ranked list. And we're basically saying, look, getting something good at the top is way better than getting something good at rank 7. And this is telling us how much better it is. And this is based on lots of modeling of people with clicks. And a lot of it is pretty arbitrary and things like that. Okay? So there's a discount function, which is how likely it is that someone is going to reach a certain rank. And then a way of translating these grades, good, whatever, into a number. And that's usually done with exponentially like this for no great reason. Okay. And what we do in these measures, here's our ranked list. The top thing is highly relevant. The second one is relevant. The next two are not relevant. The fifth one is also highly relevant. And so on. And so from each of these, we get a relevance score. So we translate highly relevant into 2, relevant into 1, and so on. Then we go through this exponential gain, and we say, okay, something that's highly relevant is actually 3 times better than something that's relevant, which is infinitely better than something that's not relevant. Then we apply this rank-based discount, which is supposed to say things lower down are not as good as things higher up. We get some numbers, and then altogether that thing gets a score of 5.46. And then, I won't show the details, but then what we do is we also add to that a normalization to say, well, what's the best possible answer you could get? What's the best possible? So you get a number between 0 and 1, right? And some of this will be talked about on Wednesday, right, in detail. But I show this to you today because you're going to try this out in the lab. Okay. All right. So here is our research volcano. I showed you an example. I showed you an example at the top of search interfaces. I talked about, if we're down in this space here, I haven't talked about what kinds of rankers and things we're going to build very much. I've only talked about how you know that you did better, okay? And I haven't touched this part at all, and I won't have a chance to touch that part at all. But everywhere on this volcano down here, the research is very much like databases, working with huge amounts of data, expressing different kinds of queries, not just text match, but entities. Do we match the town? Do we match features of the person? Things like that. How to do that very quickly across large numbers of machines. This part is more like machine learning, and this part, as you saw, is more like HCI, human-computer interaction research. Okay, let's go a little bit for a second up to about that level there, and talk about a little bit about how the pieces would fit together in a research environment. So in a research environment, here's another version of that picture I showed you, that simple picture I showed you at the beginning. We got a large collection of documents. We're going to run something low level to match the query terms against the index. We're going to bring back the top documents, okay? And then what we want to do I'm going to bring back the top documents, but if I use something really simple, TF-IDF, I don't get a really fantastic ranking. So what we want to do then, even in a research environment, is to take that and use some kind of re-ranking to improve it. Why that transition without me touching it, I don't know. I'm worried about that. But anyway, we'll just keep going. So at the lowest level, I mentioned this earlier, there's something called BM25. This has been around for a long time. It's what I call an unsupervised ranker. I think that's the best way to think about it. It does not have machine learning. You can tune it. You can make it better on collections. You'll see some tuning in the lab. But what it is, and it really just combines these features I talked about earlier, these very, very simple features. But as a baseline for research, it's really, really hard to beat this. And this actually then becomes a feature at the next level when we're doing machine learning for search, okay? And so it takes these features, you know, how often a term appears in the collection, how often it appears in the document, how long it is, and it takes all these features and mixes them together as a sum. The sum here is over the query terms, okay? There's a few extra things. This is how often the term appears in the query, right? This is where we put the inverse document frequency, and this combines. This is the frequency for a document. So this is sum over query terms t. For a particular document, how often that term appears in the query. There's a couple of tuning parameters. So that's just a number. That's what you tune there, and this b. This is the actual length of the item. This is the average length of items in the collection, and that's it. And so if you ever hear of BM25, it's just this formula, okay? But this formula works incredibly well out of the box for ranking stuff. The reason I bring it up is because you'll hear BM25 quite a lot when you hear talking about rankers. And this doesn't have any machine learning built into it, but what it has is an incredible insight into how terms work in documents, basically. You notice that that is here and there, and that for a particular document, that's just a constant. So we have basically something that looks like x over a constant plus x, okay, where x is the number of times the term appears in the document. So that if the term appears infinitely, this saturates. It actually saturates out to k1 plus 1, right? It actually, you know, if I take the limit of that as x goes to infinity, it'll go to 1. But on the other hand, if x is 1, if the term just appears once in the document, it's basically 1 over c plus 1. So it's a smaller number. So the idea is that it's not that a term appearing twice in a document is twice as good, right? A term appearing twice in a document is a little bit, and 3 times is a little bit better, but not 3 times better. Right, so this insight tells us kind of what it means to have terms repeated multiple times in documents. And this is just it's an observation similar to Zist's law that I talked about earlier, just that this seems to be how language works, and this is true for, this is how terms get repeated in stuff, and this works across all, sort of any language that's been tried on, any human language that's been tried on in lots and lots of different collections. You just have to tune those parameters a little bit. Okay, but there are limits to these, right? They're prevalent. These unsupervised ranking formulas are prevalent in document retrieval at that lowest level, but they don't have any semantics attached to them, right? They don't really understand different shades of meaning and different ways of expressing things. So what you'll see on Friday is a lot more up toward the semantic end, right? Particularly lately, there have been these very large, and I'm not going to get into details because that's an entire day of itself, but essentially language models, things that, I don't know, I'm trying to figure out a way to do this really quickly, but basically things that say, this looks like English. So I put a question by an answer. It goes, yeah, that looks like the answer to that question, both at a grammatical level, but well, not grammatical, but in every way that I can see, even to some extent, semantically, this looks like, almost factually, this looks like the correct answer. And today, if you get that far in the lab, we got a lab that goes out quite a ways. This is a model invented by Google Research, the researchers at Google, and you'll get to try that today if you get to the end of the lab. Here's Bert. What can I say about him? As I said, it's a massive pre-trained language model which you fine-tune. So you will actually fine-tune Bert today on the tasks that we'll give you in the lab. It works incredibly well for basically any known problem in natural language processing. but particularly re-ranking of passages. For longer documents, you need to do some extra work. And you'll do this in the lab, and you'll hear more about the technology on Friday, maybe. Right, Bhaskara? You like more BERT? Nah, or something similar to BERT. Yeah, a little bit. Okay. Oh, okay, that's strange. So this is, like I said, at the end of the lab, you'll get to this. We're going to adapt BERT. I said it works with many NLP tasks. We're going to fine-tune it to predict document relevance. It is almost mad. It's a huge model, right? It's trained on Wikipedia, basically. It just knows it's basically it's memorized the Wikipedia and kind of internalized how language works from that and tells you, yes, this is the correct thing. So we're going to basically, for relevance, we're going to train it as a binary classifier, and we're basically saying here's a query and here's a piece of text, how relevant is one to the other, and we'll score this, and we'll see that the scores change, right? So instead of just now, basically, we do a query, we will do this in Python, right? We'll use a tool called Answerini. It'll search the inverted index with BM25 and something else called RM3, get the top candidates, put it into this neural model, and we'll get much. So this is basically a sketch of what you're going to do in the lab today, okay? Is do this. This is what I've been talking about all day. You're going to do exactly this in the lab. We have it all set up for you, but the way it's set up is that you can play with it as much as you like afterward, okay? So we'll take you through all of the steps of using the research tools to do exactly this, but you then afterward can play with it as much as you like. Right? Okay, so that's why I actually want to go on for the next 10 minutes. By skipping all those things from my user study, I managed to catch up my time. So this is just, I'm going to end the lecture with a very quick overview of what you'll do in the lab this afternoon, okay? Basically what I did, what I showed you. So in the lab, you're going to take a document collection, and so you're not going to, to a little bit, you'll do a few exercises where you code this up yourself. But really what we want to do is work you through the research tools so that you see how the research tools are used, so then you yourself can just, typically research, you just replace one of the steps and see what the impact of that step is. So you're going to go through building an index from a document collection. You're going to take a query set and execute it against a document collection, and you're going to apply these evaluation measures, including NDCG. Okay, so NDCG was that one that simulates a person going down the list and gives you a score for how good you did your ranking. And if we have time, or if you have time, you can play with BERT. So we have this set up so that at that point where you have to fine-tune a neural ranker, that takes maybe 20 minutes or a half an hour. So if you get that far, I would ask you to find somebody who hasn't made it that far and give them a hand. Because there's only myself and Zeynep and a couple of volunteers working in the lab. So some people will power through. If you've done lots of Python and you've done lots of web development and working with research tools, you'll probably power through the lab, in which case you'll get to that spot, come and help us help other people. If you're hanging back, that's okay. We will make sure you see all the core pieces of the lab today. And then finally, we'll suggest, right at the end, if you totally run out of everything, you can try building a collection yourself. What are we going to have you work with? So this didn't come from me, actually. This came out of the University of Waterloo. It's actually somebody else, another faculty member. When I was in Facebook for a couple of years, he basically took almost a commercial level search system called Lucene that's open source. And there's some of those things I showed you run off of Lucene in reality. But this is Jimmy Lin. Zeynep's actually was his student. It's called Anserini, and I'm just showing you the picture there. You get the URL when you on the slides, and it's basically taking search engine tools and making them research oriented. So you're going to work with Anserini. It says open source information retrieval toolkit built on Lucene, which is a commercial quality but open source system, and it aims to bridge the gap between academic information retrieval research and the practice of building real world search applications. So that's what you want to do for research, is to bridge that gap. So you're going to be working with Anserini. Rather than, so actually you will need if you don't have a Google account, you will need one. Because we're going to use something called Google Colab. So remember so this lets you run, if you've run Jupyter notebooks and things like this for Python, some people have done that. This is, and some people may have used Colab. This is actually Jupyter notebook running on Google's computers. So I would say running in the cloud, but if you didn't know before, now you know that when we say running in the cloud, we mean running on a computer in a data center owned by Google. Okay? So there's no different. Something's running in the cloud. It's not doing anything different than running on your laptop, except it's somebody else's laptop. Well, not laptop, but it's somebody else's. Okay? And it's probably a virtual machine running on their machines, but that's what it is. It's running in a data center. And so Colab lets you run Python on Google computers, which means that we don't have to have enormous resources here. Then there's a certain level of sort of free or relatively inexpensive. I think the lab today is costing us like $5 a person or something, which is still money, but it's a little cheaper than buying a lot of computing equipment. So you'll be using Google Colab. So we have a full tutorial built. If you've never used these notebooks before, so what you'll do, this is the start of your tutorial lab today, and we're going to start with a quick introduction to the notebooks itself. If you don't understand this at all, you can get some tutorials there, or you can plunge right into it. But the basic idea, if you've never used a Jupyter notebook or a notebook before, is you have these boxes and you actually write Python code directly in the box, right? So, and this is only for people who've never done this before. So you can write some Python code in there. What we're going to have you do is change hello world here to your name, and then you just press run there, and it goes out to Google's computers, and it runs the Python code. And I changed it to Charlie Clarke, and it does that. So now what you can do is you then have, and the nice thing about this is that web page is a virtual machine. It's a computer running out in the cloud, i.e. in Europe in Google's data center, right? It's running in the cloud, and you can't hurt anything. You can play, if you're unhappy with what you're doing, you go to the top, you say, run from scratch, and it will just basically blow up the virtual machine and let you have a new one, right? So you can never do anything wrong with this, because you can always start from the beginning again. But it's like a computer. It's going to have a file system. If you click on that tab up there, okay, you'll be able to see the files in your file system, okay, as you go along. Please write this down. There's a long bunch of stuff, or you can just get it, like it's on the thing, right? The slides are on the thing. You can get it out of the thing, or you can just take a picture of it. That's the key thing you need to know to do the lab. You have to go to that site, and then you'll get this page, and here are the activities, an introduction to Python for information retrieval. So that's pretty, and that'll end with a little build an inverted index exercise. So you can make a decision. If you've done lots of Python programming in notebooks, you should go through that quickly. If you haven't, you should go through it slowly and make sure you understand all the pieces, okay? And then there's an indexing notebook, and then there's a querying and retrieval, and then there's a re-ranking notebook. So everything I showed you here today is going to be there. So you go to that location. I'm going to leave it up there for another couple of seconds. and you start by clicking on Python for IR there, okay? So you click right there, that's where you start, okay? And that will take you to a page like this. And I'm doing this very carefully so that, because I want you all to at least get started without any trouble, okay? So you click there, and then if you've never run Collaboratory, so this is still GitHub, okay, and quick introduction, and then you click there, okay, that's important, that you may not notice that. So when you can't, this will look like, see, it's got the Python cell, it looks like a notebook, but you can't run it, it's just non-executable code. But if you open it in Colab right there, then, and then when you open it in Colab, you'll get this scary message. Okay, it says, you know, warning, this notebook was not authored by Google. Okay? And you click run anyway, because it was authored by Zeynep, and she's very nice and isn't going to hurt anything. Okay? All right. So I just wanted to go through those steps, right, to make sure that people can get, and then the notebooks themselves should tell you how to move forward, and we're all going to be in the lab, and we should all get to the point where we're tuning a ranker and stuff like that. Okay, that's all I had, and see, I managed to land it, except I can take a couple of questions, right, and then we can actually try this out. We can have lunch, right, and then we can try it out. So any more questions about anything? Yeah, okay, sorry, yeah. So there are computers in the lab. If you want to do it on your laptop, that's fine, because it's all built into this, it's all built into the notebooks. So if you want your own laptop, you can use it. If not, you can use the computers in the lab. It's all going to be the same thing. You will need a Google account, that's all. So if you got Gmail or any of that, that's already fine.
Now, in case we don't want to use our laptop and we decide to use the computers in the lab, at least the hands-on we are going to get there when we get back home.
So when you get back home, as long as you have the Google account, yeah, you can still access these.
Yes.
Yeah, and you should be able to have, they don't use that much resources, so I think you should be able to, or they cost minimal. I know some of it is free up to a point, then you pay a little bit to resources, okay? But this should be something you should be able to do anywhere in the world, right?
I want to ask a question from what you talked about.
Sure.
Taking you back a little bit.
Sure.
When you were talking about STEMI,
Yep.
the other time, you said in the industry they do that with a lot of carefulness.
Yes.
Right. I wanted to find out if, when doing that, when trying to want to exercise that level of carefulness.
Yep.
Okay. Are there rules or laws that should not be violated? Or you just do it based on instinct, or
So that's actually a good question.
or
So, and that's why I think this is a really good point about the difference between industry and academia. So in academia, you're doing one of these research collections, right? You're doing one of these challenges or benchmarks or something, right? So your goal is to try to get the score in the benchmark as high as possible. So generally speaking, if you apply a Porter stemmer, something that's English, or there are ones for other languages, and sometimes it's quite hard, right? So you know, Doug is really the expert on this, but Arabic is quite difficult to get the stemming right, okay? But there are tools available, you just apply them, and they will make your score better, okay? So if you're in academic research, that's okay. If you're in industry, then you would have like a separate query understanding team. And they would, so it's not just one rule, they would build whole sets of rules from user data, from linguistic sources that would do, so this is not, unless this is the thing you're doing for research, you don't worry, you just apply the stemmer. Okay, right. If it's a thing you do for research, then yes, you start to look at linguistic sources, you start to try to figure things out. But the goals in industry and academia are different in this area. And in industry, you want to tailor the query understanding component to exactly, you're doing e-commerce search, so you tailor it exactly to that. You do web search, you tailor it exactly to that. So it's just a split between what's done. So if you go to a commercial environment, you never assume that you can do stemming. They don't do that. But you do it for research because you're going to get a benefit out of it from a research standpoint. Okay. Yeah.
Thank you. I guess you're using Bing for your search.
Me? Yeah. I use Google. Oh, some of these examples?
Oh, yeah. Okay. For Google search engines, when you search, you get some results that are more of like adverts.
Yep.
So do you rank that with all these explanation you think actually?
Right. So being that you adds to, all search engines are going to do, well, search engines that aren't trying to sell you something, they're going to do ads, right? Not I think DuckDuck. Well, anyway, there's going to be advertising. So that's always done by a separate team. Okay. So there's going to be a large team that's doing the search engine and a separate team that's doing ads. Okay. And they're only blended together right at the end. Right. So Google, any of those things, and they should be labeled, not as well as they are. Yep. 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 Oh yeah, there are two. So in the company, those people won't even. They might not even be in the same location, right? They will. The ads team and the search team are totally separate groups, and then they're put together right at the end. The ads team decide, oh yeah, I want to put some ads on this search. They put some ads on the search, but then the word is the organic. So the people that are doing the search results that are not advertising, they're usually called the organic results. And then there's the advertising, and you put those together. Yep.
For the unsupervised rankers,
yep.
You made mention of DM25. I'm actually hearing that for the first time. But where can we classify the random forest?
So random forest is actually the next level up. Right? So what I was talking about, learning from flipping things around, that's like typically a random forest is a sort of classic way to do a machine learning. So that would be the next level up. So BM25 works at a very low level, right? You just tune it to what your application, right? There's no training data. To do a random forest, you need a lot of labeled training data, right? And so actually random forest is a pretty standard, before neural rankers became more popular, and they're still only used toward the end. Like typically that middle level is going to be a random forest, right? Okay, that's great. Any more questions of this? Yeah, just a quick one. Yep.
I understand you're going to Facebook.
So I was at Facebook. I'm not. I'm at the University of Waterloo now. So I have nothing to sell whatsoever, right?
Just a quick one with regards to considering that you are dealing with a lot of unstructured data.
Yep.
Which is just a lot of it.
Yep.
Petabytes. And I understand Facebook kind of they use HBase.
Yep. They use a lot of different things actually. Okay. Almost any kind of tool you've heard of is used in there somewhere.
I just wanted to ask in terms of performance tuning, especially with the indexing.
Yeah.
Were there any methods you were using for performance tuning? Because I know with the big table, with the key,
yep.
the key
value store. Yeah.
Very critical in terms of how you design them for performance tuning. Is it the same case with the experience?
So one interesting thing is that as far as tools that are meant for other database applications don't work well for search engines. Okay. So search engines are usually, if you're looking at the scale of something like Google or Microsoft or Yandex or Facebook, you're looking at a search engine that's been usually custom written, right? And it's the low-level indexing is the performance is really critical. So they don't usually depend on something like a key value store for that. That's usually done, at specialized teams that are writing it in C++ and are writing it mostly for performance rather than but it's the same kind of thing. There's a bunch of parameters that need to be tuned, but not just from the ranking standpoint, but from block sizes and how the compression is done and all that kind of stuff, right? So there's a whole bunch of research in search engines and recommendation, which is like database research. Right? There's a lot about compression, a lot about rapid access, about different layers of caching, about how to organize clusters of search nodes, right? So there's sort of three levels from a research standpoint, and from a development standpoint. There's like a database layer essentially, which is unsupervised rankers and block sizes and things like that. There's this learning to rank level, which at the bottom is usually a random forest or something, long feature vectors, and farther up is neural ranking and things like that. And then at the top there's HCI issues about, how does it impact people? How do you lay things out? Where do you put things? How big should captions be? What should be in the captions, right? So it's actually a really complicated set of things, putting one of these things together, right? Something like building a search engine from scratch now is kind of major challenge again. And I'm even leaving out all the pieces of like the ad system that has to come in and the maps that have to come in and the images. So so it's all very, but so HBase is, so that's a good example of, no, you probably wouldn't build a search engine on top of HBase, right? You build other things, on top of that, right? Okay. And then I miss crawlers too. So, all right. One more question, or should we go to lunch? Lunch. All right. Thank you.
Until 1, and the lab will start at 1, roughly at the second level here as well, on the second.
So lab is, do they go right that way?
You go down the alley here, and